Now it remains for us to prove this lemma from linear algebra. If A is an n by n real matrix with trace equals 0, then A is R orthogonally similar to a matrix with 0 diagonal entries. To this end, we let A be a matrix with 0 trace. If its diagonal entries are all equal to 0, then we are done. This is what we want to prove. If not, then there exists a sub jj not equal to 0 for some j not equal to I. This is because our assumption that trace of A is 0. The sum of diagonal entries is 0. If 1 is 0, there must exist another one that is non-zero. And furthermore, there should exist such a sub jj which has opposite sign to A sub I, namely the product is negative. So now, without loss of generality, we may assume that I is 1 and j is 2. Next, we're going to find a conjugation for this matrix that will annihilate A sub ii and A sub ij, which by assumption is A sub 1, A sub 1, and A sub 2, 2. So now we are looking at the matrix, and we consider the conjugation of this matrix by this guy. So this matrix consists of zeros, ones, and this 2 by 2 matrix that corresponds to a rotation in R2. Cosines, negative sign, sine, cosine. Those diagonal entries are ones, and the other entries are 0. And this one is transpose and inverse. This is clearly an orthogonal matrix. Now we compute this conjugation. What we do is that we are going to focus on the 1, 1 entry of the product of those three matrices. So this is the 1, 1 entry of the new matrix. And we have A1, 2 prime, A2, 1 prime, and A2, 2 prime. And observe that A3, 3 prime will be equal to A3, 3, all the way to AN prime, which will be equal to AN. They are preserved. We don't know the other entries. We don't have to compute them. Let's just focus on the diagonal entries plus those two elements. Because this theta is a parameter to be determined. Theta can be any real number. We'll be interested to know if there exists a theta that will make this element, this A11 prime, vanish. Can we find the theta that will make this expression vanish? The answer is yes, because we can now pull out a cosine theta square. So this becomes cosine theta square times this expression. Here, we know that tangent theta has range the whole real line. So you can view this part as a quadratic function of a real variable. And this part cosine theta is bounded by 1. So if you can find a real number, the tangent theta, that will make this part vanish. Then we are done. Here, don't be silly saying that you can just plug in theta equal to pi over 2, because in that case, although this part 0, this part is infinite. 0 times infinite. Weird. Actually, if you plug that theta equal to pi over 2 to here, you get a finite number which may not be 0. Now, since we have assumed that A11 times A22 have opposite signs, the product is negative, we know the discriminant is a positive number. So there exists a theta such that this expression is 0. There is a real solution. And this answers our question. We can find theta that vanishes this part. So we can carefully choose a theta that will make the first entry vanish. But we know those entries, those n-2 entries, are the same with the original matrix. So if they are 0, non-zero, same will happen for those entries. And we also know that our assumption A22 is always non-zero. So no matter A22 prime is 0 or not, this guy always has one more 0 entry on its diagonal than this matrix. So this conjugation does create one more 0 entry on its diagonal. So with a careful choice of theta, we can create at least one more 0 diagonal entry through the conjugation as we described above. When I say at least one more, actually I mean one more or two more. But that is okay, because there are only finite many entries on the diagonal. There are only n many entries. If we repeat this procedure for no more than n-1 times, then we can make everybody on the diagonal vanish. Through conjugation. So, by repeating this procedure, or by induction, we can prove this lemma. What we do is that we keep conjugate this matrix A with orthogonal matrices. The product of orthogonal matrices is again orthogonal. So we are safe with this method. We have finished proof of this lemma. And with help of this lemma, we finally finishes the step number 3, and thus the solution to this question. The question of finding the radius of the largest k-dimensional ball inside the n-dimensional unit hypercube. The largest radius is 1/2 times square root of n over k. We scale it by a factor of 2, and we need to scale it back by multiplying 1/2. So we are done.